Most parents buy a robotics kit hoping their kid will learn to code. 3 months later, it's gathering dust because jumping straight into Python syntax killed all the fun. There's actually a proven path from visual blocks to real programming, the same Python running factory automation and data science pipelines, and it takes about 18 months if you do it right. My name is Rajiv Patel, and I've taken both my kids through this exact progression.
You're listening to the STEM Lab podcast. Quick heads up before we get rolling. Everything you're about to hear is researched, written, and verified by real people, but the voice delivering it is AI generated, just so you know what you're listening to. If you've been tuning in for a while, thank you. It's genuinely great to know this stuff resonates with you. And if this is your first time here, welcome aboard. We release new episodes every Monday, Wednesday, and Friday, breaking down practical STEM tools, curriculum ideas, and hands-on projects that actually work. Today, we're getting into how to teach Python and block coding using LEGO robotics platforms. Let's get into it. LEGO robotics platforms offer something most coding tools miss entirely. You get to see your program work in the physical world within seconds. A sensor reads light, motors spin, your robot moves. That immediate feedback loop is what keeps kids engaged long enough to actually learn computational thinking, not just memorize syntax. This guide walks through a 3-stage progression using WeDo 2.0, Spike Prime, and Mindstorm's Robot Inventor. The sequence moves learners from icon-based programming around age 7 to legitimate Python development by age 12. We're talking about the same Python used in professional software environments, not a dumbed-down toy language. You don't need prior programming experience to teach this. What you need is basic computer literacy, patience for 45 to 90-minute sessions, and a willingness to stick with a structured curriculum for 12 to 18 months. The measurable outcomes are real: block-based logic in 6 to 8 weeks, Scratch-equivalent programming in 12 to 16 weeks, and Python fundamentals, including object-oriented patterns, in 24 to 32 weeks. Let's talk about what you'll actually need. For hardware, you're looking at 3 platforms in sequence. WeDo 2.0 is for ages 7 to 9. It's got Bluetooth connectivity, 280 pieces, a motor, and tilt and motion sensors. Then you move to Spike Prime for ages 10 to 13. Check the link below to see the current price. It's got a hub with 6 input-output ports, supports both Python and Scratch, and includes 523 pieces with distance, force, and color sensors. Finally, there's Mindstorm's Robot Inventor for ages 10 and up, with a programmable hub, 4 motors, 949 pieces, and full Python compatibility. On the computing side, you'll need Windows 10 or 11, macOS 10.14 or newer, Chrome OS or iPadOS 13 or higher, Bluetooth 4.0 or USB connection, 2 gigs of RAM minimum, and a gig of free storage. Verify your specific operating system compatibility on LEGO Education's official support page. The software is all free. You'll use the WeDo 2.0 app for icon-based work, the Spike app for block and Python modes, and either the Mindstorm's Robot Inventor app or a Python IDE like VS Code or Thonny for the advanced stage. Beyond that, set up a dedicated workspace at least 90 by 60 centimeters. Each hub needs 2 to 3 hour charge cycles, so plan your USB charging infrastructure accordingly. Challenge mats or task cards help structure objectives. See the STEM Toy Lab Setup checklist for power and expansion planning details. Prerequisites are minimal. The learner needs to follow multi-step assembly instructions, handle basic mouse or touchscreen navigation, and have adult supervision if they're between 7 and 9. By age 10, independent work becomes feasible. Now, let's establish the foundation with block-based logic using WeDo 2.0. You start with icon-based programming because it builds cause and effect relationships without syntax getting in the way. WeDo's visual interface eliminates text barriers while teaching the core concepts: sequential execution, event triggers, loops, and sensor conditionals. Install the WeDo app and complete the Milo Starter project. It's a wheeled robot that responds to tilt sensor input. This builds familiarity with program flow: green start block, motor activation, sensor conditional, output response. The platform's limitations are intentional. There are no variables, no custom functions. That forces focus on algorithmic thinking rather than wrestling with language syntax. Here's the curriculum progression for this phase. Weeks 1 and 2, direct motor control and single input triggers. Weeks 3 and 4, loop structures, like repeat until sensor threshold. Weeks 5 and 6, dual sensor logic, using chained blocks for and or conditions. Weeks 7 and 8, a capstone challenge, requiring 3 or more sensor inputs and conditional branching. The capability milestone you're looking for is this. The learner independently designs a program with at least 1 loop, 2 sensor inputs, and predictable behavior across 5 or more test runs. That indicates readiness for variables and text hybrid environments. WeDo's offline functionality is a big advantage. Programs transfer via Bluetooth and execute locally on the hub, no cloud dependencies. Battery life averages 6 to 8 hours of active use, so plan for mid-session charging during longer builds. Once that foundation is solid, you transition to Spike Prime's hybrid block Python environment. Spike Prime introduces variables, custom functions, and data structures while maintaining visual block scaffolding. The app offers side-by-side block and Python views. Learners see text equivalents of their block programs in real time, which is the cognitive bridge that makes everything click. Begin with Spike's competition-ready training modules. These parallel competitive robotics challenges. First, LEGO League uses Spike Prime hardware. The projects require data storage through variables, reusable code segments through functions, and sensor array processing. You couldn't do any of this in WeDo's icon-only environment. Here's the critical transition exercise. Build the line-following challenge using blocks, then switch the app to Python view. Learners observe that a repeat until block becomes a while loop. A motor run for degrees block becomes motor.run_for_degrees with a number in parentheses. Block variables become speed equals 50 declarations. Run the program in both modes to demonstrate they're functionally identical. This is the moment where blocks stop being a separate thing and become Python with different syntax. That realization demystifies text-based coding. The curriculum for weeks 9 through 16 goes like this. First, recreate all WeDo projects in Spike blocks to demonstrate that logic is transferable. Then, modify one parameter per program using Python view. Change motor speed values, for example. Next, write one new function in Python that doesn't exist in the block library. Finally, complete a full program in Python without touching the block interface. Spike's hub has 6 ports, so you can run simultaneous sensor arrays: distance, color, force, gyro. This enables multi-input programs that mirror real automation systems. Storage capacity holds 20+ programs. Expect to have a lesson on hub memory management around program 15. By step 3, you implement Python-first programming with Robot Inventor. Mindstorm's Robot Inventor runs MicroPython, which is a Python 3 subset optimized for microcontrollers. This isn't a toy language anymore. It's the same Python governing enterprise automation, data science pipelines, and robotics control systems in professional environments. Configure the development environment for text-based work. The beginner path uses the Robot Inventor app's Python canvas with built-in error checking and autocomplete. The advanced path installs VS Code with the PyBricks extension for a professional IDE experience. The first Python native project is porting the Spike line follower to Robot Inventor using raw Python, no block conversion. This forces proper syntax, whitespace management, and manual library imports. You're writing code that imports libraries, instantiates objects, and runs a while loop checking sensor values to control motor pairs. It's real programming. The learning objectives for weeks 17 through 32 are mastering library imports and object instantiation, implementing custom functions with return values, using lists for sensor data logging, applying PID control logic for precision navigation, debugging programs using print statements to the hub display, and structuring multi-file projects with modular code organization. Robot Inventor's 949-piece inventory supports complex mechanical builds that require sophisticated code, multi-axis arms, parallel processing for simultaneous motor control, interrupt-driven sensor handling. These scenarios demand programming patterns identical to industrial automation. By week 24, you bridge to industry-standard development practices. This is what separates LEGO programming education from toy-tier experiences. Introduce version control fundamentals. Save program iterations as dated files, line_follower_v1.py, line_follower_v2.py. Discuss why this matters in team environments. It prepares them for Git introduction in later coursework. Enforce commenting discipline. Require inline comments explaining algorithm logic, not obvious syntax. A poor comment says, turn motor on. An effective comment says, reduce left motor 60% to compensate for weight distribution imbalance.
Teach function decomposition. Break programs exceeding 50 lines into discrete functions, sensor reading, decision logic, motor control as separate callable units. This mirrors professional module design. Introduce edge case testing. Deliberately test programs under failure conditions, blocked sensors, low battery, obstacles. Document observed behavior versus expected outcomes. This debugging mindset translates directly to production software quality assurance. Connect LEGO work to career track progression. After mastering Python on Robot Inventor, learners can transition to Arduino robotics kits using C++, then ROS, Robot Operating System, on Raspberry Pi platforms. The algorithmic thinking, sensor fusion logic, and control system concepts remain constant. Only syntax changes. Now, let's talk about integrating cross-platform capabilities. LEGO programming scales beyond standalone robotics through hardware interfacing and protocol expansion. Spike Prime and Robot Inventor support UART serial communication, which means you can connect Arduino or Raspberry Pi boards via serial protocol for hybrid projects. LEGO actuators controlled by Python running on external compute. You can integrate third-party sensors, ultrasonic arrays, IMU modules, LiDAR sensors through analog and digital input-output ports. This requires manual sensor polling and data parsing, which brings in advanced Python list comprehension and mathematical operations. Both platforms support Bluetooth API calls. Write Python programs on a laptop or tablet that remote control LEGO hardware. This introduces client-server architecture concepts. Here's an example hybrid project. Build a LEGO robotic arm controlled by a machine learning model running on an external computer. The model processes camera input for object detection, sends movement commands via Bluetooth to the Spike hub, which executes motor sequences. You're combining computer vision, network protocols, robotics control, and mechanical design. That's legitimate systems integration work. For expansion planning, budget for supplemental component packs. The Spike Prime expansion set adds 603 pieces for about $100 to $120. Each expansion enables new mechanical challenges requiring code refactoring. Gear ratios change motor timing calculations. Additional sensors demand array processing. For learners demonstrating Python competency, meaning they can write 100-plus line programs with functions, loops, and error handling, transition pathways include CAD design curriculum for custom LEGO-compatible parts, 3D printing workflow to manufacture specialized components, and Arduino IDE migration for microcontroller programming without LEGO's abstraction layer. You need to assess skill mastery through progressive challenges, not seat time. These benchmarks indicate genuine skill acquisition versus superficial familiarity.
For block-based proficiency in the We Do phase, look for learners who independently debug programs with 10-plus blocks without adult intervention, predict program behavior before execution with 80% or better accuracy, and modify existing programs to achieve new objectives without starting from scratch. For hybrid transition competency in the Spike Prime phase, they should read Python code and explain execution sequence verbally.
identify syntax errors in 20-line programs within 5 minutes, and write custom functions that accept parameters and return calculated values. For Python native mastery in the robot inventor phase, they should structure programs with 3 or more discrete functions, implement list operations like append, sort, and filter for sensor data, debug logic errors using print-based variable inspection, and complete 100-line programs requiring multi-file imports and object-oriented patterns. For advanced integration in the expansion phase, they should interface LEGO hardware with non-LEGO components requiring custom protocols, design programs with error handling using try-except blocks for sensor failures, and optimize code for performance, reduced latency, efficient battery usage. These milestones map to concrete skill outcomes in STEM career preparation, not arbitrary age-based expectations. A motivated 9-year-old can reach Python native competency. A disengaged 13-year-old may plateau at block-based work. Structure curriculum around demonstrated capability, not birth date. I ran both my children through this exact progression. The younger one started at age 8 and reached autonomous Python programming at 24 months. The older one started at age 11 and achieved the same milestone in 14 months. Prior exposure to logical thinking, chess, strategy games correlated more strongly with progression speed than chronological age. Let's establish maintenance protocols and long-term infrastructure. LEGO Robotics platforms demand organized infrastructure to prevent the $400 pile of parts failure mode that ends most STEM initiatives within 18 months. For component management, sort pieces by category: beams, connectors, sensors, motors, using compartmentalized storage. Label bins with part numbers from LEGO's digital building instructions. Budget 45 to 60 minutes monthly for inventory organization. Chaos accumulation kills momentum. For battery discipline, Spike Prime and Robot Inventor hubs use integrated lithium-ion batteries, no AA waste. Expect 500-plus charge cycles before capacity degradation. Replace hubs approximately every 3 to 4 years under regular use. USB charging requires 2.5 to 3 hours. Maintain 2 robots in rotation to eliminate downtime.
For the software update cycle, LEGO releases firmware updates quarterly with bug fixes and feature additions. Schedule updates during non-project periods. Expect 30 to 45 minutes for hub reflashing and app synchronization. Backward compatibility issues are rare, but document current firmware version before updating. For consumable tracking, LEGO elements withstand 1,000-plus assembly cycles, but high-friction parts like gears and axles wear noticeably around 500 cycles. Track usage on competition-level robots requiring precision tolerances. Replacement parts are available through LEGO Education customer service at individual component pricing. For connectivity troubleshooting, Bluetooth pairing failures constitute 70% or more of support requests. Standard protocol: power cycle the hub, force quit the app, repair from device Bluetooth settings, not in-app. USB fallback is available on all platforms. For home lab integration, see the complete setup requirements covering workspace dimensions, power distribution, and environmental factors. Temperature extremes degrade battery performance. Humidity risks electronic corrosion. Now let's map learning outcomes to career-relevant competencies. LEGO Programming Education's return on investment emerges in skills that transfer directly to professional software development, not robot driving abilities. These competencies appear in actual job descriptions. Computational thinking means decomposing complex objectives into discrete algorithmic steps. This mental model applies to financial modeling, data pipeline design, infrastructure automation, anywhere process logic matters. Abstraction is recognizing when to write reusable functions versus duplicating code. Professional code bases fail when developers can't identify appropriate abstraction layers. Debugging methodology is systematic hypothesis testing when programs produce unexpected results. Most software development time goes to debugging, not initial coding. LEGO's immediate physical feedback builds this diagnostic discipline earlier than screen-only platforms. Sensor fusion logic is processing multiple simultaneous inputs to inform single decisions. This is identical to IoT device programming, autonomous vehicle systems, and industrial automation controllers. State machine design manages robot behavior across different operational modes. This pattern governs embedded systems, game engines, network protocol handlers. It's a fundamental computer science concept often introduced too late in traditional curriculum. Compare this to skill progression in other robotics platforms. VEX scales to higher mechanical complexity but maintains proprietary software. Arduino offers unlimited expandability but lacks structured curriculum. LEGO's educational pathway provides scaffolded progression from visual programming to production Python, then facilitates exit to other platforms once core competencies solidify.
The learner who completes this curriculum can read and modify Python programs in professional code bases with mentorship, understand embedded systems documentation and sensor datasheets, collaborate on GitHub repositories following basic version control, and transition to specialized robotics frameworks like ROS or ArduPilot with reduced onboarding time. These aren't future possibilities, they represent current capabilities. I've placed children completing this progression into high school robotics teams where they immediately contribute to competition code, bypassing the 6-month ramp typical for beginners. Here are some pro tips and common mistakes to avoid. Start block-based irrespective of the child's age. Parents with programming backgrounds frequently skip WeDo and thrust 10-year-olds directly into Python. This creates syntax struggles that mask underlying logic deficiencies. 3 weeks in a block environment establishes algorithmic patterns. The Python transition afterward takes days instead of months. Enforce the no touching during execution rule. Physical intervention while programs run prevents learners from observing cause-effect relationships. Programs must complete or fail autonomously. Exception: immediate safety concerns only. The common failure pattern is jumping platforms before mastery. Moving from Spike Prime to Robot Inventor because they seem bored usually indicates challenge deficiency in current curriculum, not platform limitation. Spike Prime supports programs of arbitrary complexity. Add multi-sensor fusion challenges or competitive robotics problems before upgrading hardware. For battery management discipline, dead batteries during project sessions destroy engagement. Maintain a charging schedule regardless of visible battery indicators. Hub batteries degrade non-linearly. A 60% indicator may represent 15 minutes of actual runtime. Use version control from day one. Save every program iteration with descriptive names and dates. Why didn't my old program work? Scenarios provide teachable moments about code documentation and systematic testing. Delete nothing until project completion. Avoid the subscription trap. LEGO education apps require no ongoing subscriptions as of 2026. Third-party curriculum providers may charge $10 to $30 per month for lesson plans. Evaluate whether structured content justifies cost versus free community resources and official challenge cards. Set screen time boundaries. LEGO programming education involves 60 to 70% screen interaction, 30 to 40% physical building. This isn't hands-on learning by traditional metrics. Set explicit screen time policies and enforce building-only sessions to maintain tactile skill development. For completely screen-free foundations, consider unplugged coding progression before introducing LEGO Robotics.
Let's hit some frequently asked questions. Can we start with Spike Prime and skip WeDo if my child already knows Scratch? Yes. Scratch competency, loops, conditionals, variables, indicates readiness for Spike Prime's block environment. Start with Spike's intermediate challenges rather than beginner tutorials, then transition to Python View within 4 to 6 weeks. WeDo's icon-based system offers minimal value for learners already comfortable with visual programming abstractions. Test readiness this way.
If they can independently write a Scratch program with custom functions and conditional logic, WeDo becomes redundant. Which platform supports the transition to text-based Python fastest? Spike Prime's side-by-side block Python view creates the most efficient cognitive bridge. Learners see direct equivalence between visual and text representations in real time. Robot Inventor offers more advanced Python features, object-oriented programming, list comprehensions, but lacks the scaffolded comparison interface. For learners ages 10 to 11, start Spike Prime and migrate to Robot Inventor once they're writing 50-plus line Python programs independently. For ages 12 and up, Robot Inventor's Python native approach works if they've completed any prior block-based curriculum. Do these platforms require internet connectivity to program? No. All LEGO education software downloads programs to hubs via Bluetooth or USB, then executes locally without network dependency. Initial app installation and firmware updates require internet. Ongoing programming and robot operation function fully offline. This architectural choice makes LEGO Robotics viable in bandwidth-limited environments and eliminates cloud service outages as failure points. Contrast that with cloud-dependent platforms that become inoperable during connectivity issues. How does LEGO Programming Education prepare kids for Arduino or Raspberry Pi projects? The algorithmic thinking, sensor input processing, and control system logic transfer directly. Only syntax and hardware interfaces change. After mastering Python on Robot Inventor, learners understand program structure, variable management, function design, and debugging methodology. Arduino introduces C++ syntax and direct register manipulation. Raspberry Pi offers a full Linux environment and unlimited processing power. Both require the same computational thinking LEGO develops, with reduced abstraction and increased hardware complexity. Plan a 6 to 8 week transition period for syntax adjustment when moving to Arduino-based robotics platforms after LEGO mastery.
To summarize, LEGO Programming Education provides structured progression from icon-based logic to production Python across 18 to 24 months, using hardware platforms that scale complexity while maintaining consistent programming paradigms. The WeDo to Spike Prime to Robot Inventor pathway develops computational thinking, algorithmic design, and debugging discipline that transfers directly to professional software development environments. The platform's value proposition centers on immediate physical feedback. Programs produce observable mechanical outcomes within seconds, creating faster iteration cycles than screen-only coding platforms. Combined with offline functionality, expandable hardware architecture, and direct Python compatibility, LEGO Robotics serves as legitimate technical infrastructure for progressive STEM learning paths, not entertainment-focused toys. Budget $300 to $800 for complete platform progression, plus 90 to 120 minutes weekly for structured learning sessions. Expect measurable Python competency within 24 to 32 weeks for learners starting Spike Prime at age 10 or older. This timeline assumes consistent practice, adult facilitation during early phases, and project-based curriculum rather than passive tutorial consumption. The learners completing this progression possess demonstrable skills matching first-year computer science undergraduate competencies in algorithmic thinking, basic software architecture, and embedded systems logic. That's verifiable through code samples and portfolio projects that separate genuine capability from credential inflation.
That wraps up this episode of the STEM Lab podcast. Thanks for listening. New episodes drop every Monday, Wednesday, and Friday, so there's always something new coming down the pipeline. If this was helpful, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It genuinely makes a difference in helping other people discover the show who are looking for exactly this kind of content. And hit subscribe or follow so you get notified the second a new episode goes live. Appreciate you being here. Talk soon.